All right, received a few questions this morning. The first one is about converting. Goodness, you're off a little bit today. Sorry. First one was talking about how to go from the stereo projection drawing to the stereo drawing. So how are they defined in the packets? To go from the 2D projection to the stereo drawing. So this is honestly the hardest part because the 2D projection has the axial and equatorial positions, whereas the 2D drawing doesn't. So just a quick refresher, this 2D stereo drawing here is actually a projection. So if we took the six-membered carbon ring and we cast a shadow onto the board here, let's see if I can get it to work. Nope. So if you cast a shadow onto the board, the shadow you end up getting is this 2D structure here. This is where we get the axial and equatorial. And I've seen books differ on how they draw this. So if mine varies from other books, don't worry. I assure you we can find another book that would actually agree with it. But anyway, way I was taught, your axial positions are going to be up, down, up, down, up, down. And then your equatorial positions here, some will actually draw them like with that gauge confirmation up, down. Personally, I found no use to doing that. Your equatorial, they point out. So out, 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 and out. So we have the axial and equatorial positions, and what we're trying to do is we're trying to convert it back to this 2D drawing that doesn't have these axial and equatorial. So we have to use the cis, we have to somehow backtrack how this goes to cis trans. So the way we do that is, actually the easiest thing to do is just to build your 2D model or build your 3D model and go back off of that. But let's say you don't want to build the model. So what I'm going to do is I'm going to, first packet problem, to ask about this. Where's my eraser? There you are. As an axial, and an equatorial. And we want to look at the stereo drawing. So what I like to do is always define this as carbon 1 and this next one as carbon 2. It just kind of helps simplify things in terms of like consistency. You wouldn't be wrong if you drew things rotated, and this is where that, the rotation symmetry through the center of the ring kind of helps. But anyway, so let's say, so I've got my cherry confirmation, and I've got an axial, and an equatorial. So if I build my cherry confirmation and I rebuild it from this 2D stereo projection, this is what I end up with. I've got the two axials coming up, and then I've got the one equatorial. So now all I do is I take my ring and I push it down until it's a flat ring. And so what I see is I've got three cis's. Now, how do I know that these are all cis's? How would I know that without looking at the drawing or without building the molecule? So to do this, and again, this is much harder. This is why I would highly encourage you to use your modeling kits. Draw this a little bit clearer. Oops. Sorry. That's right. Easiest way to draw these. You draw two parallels. Draw your diamond down, your diamond up. So the way I see it when I go off these projections. So this is what I have here, the black ones. And then what I do is I fill out the axials in my head because they're the easiest ones to see. So I'm going to fill out all the axial positions that aren't labeled here in blue. So this one's already filled in. This one would go down. This one's already got a methyl group, so that's a hydrogen. This axial goes down. This axial goes up. This axial goes down. Now the thing is that if I have an axial, every other axial is going to be cis. So these three that are pointing up are always cis. So if I see these two methyl groups pointed up, I know that they're cis. If I ever have axial groups pointed in the opposite direction, they're going to be trans. So make sure I said that correctly. Yeah. So off the bat, I know that these two axial groups are cis because they're both axial and they're on the same side of the ring. So when I take these axial groups, these three axial groups that point up, whenever I crush this ring down, they always end up being cis. Now if I have the opposite, if I have the three axial groups pointed down, there's no way that axial groups on opposite sides of the ring are ever cis. They always have to be trans. That's how they end up on opposite sides of the rings. So I go off the axials first to figure out who's cis. Now for the equatorials, we're going to look at what they are relative to this first methyl group. Well, we look at whether the axial group is above or below. So if the axial group is below, it's going to pop up when we flatten out this model. So it's going to be cis with anything that's pointed up. If we have an equatorial where the axial group is up, it's going to get pushed down. So to kind of demonstrate this, here are my two equatorial groups. And I got one where I've got an axial group up and an axial group down. And when I start crushing this down into the 2D projection, what ends up happening is if my axial group is up or is above it relative to the ring, what it's going to do is when I crush out this ring, it's going to push the equatorial position down beneath the ring. If I have the axial atom beneath the equatorial atom, when I go to push that into the shear conformation, it's going to push the equatorial atom up. Because keep in mind, the equatorial positions here refer to the equator. So even though books do try to correctly draw it with the equatorial groups like zigzagging their gauche to each other, honestly, they're called equatorial because they're on the equator. So you can just think about them as sticking out, and the axial groups being pointed straight down. And then when we actually start bending it to truly get to what we'd expect to see for this like flat 2D ring, that's when you start seeing which side of the ring they're on. Sorry, this is a hard thing teach you how to do directly off the picture. So for this example here, all three are cis. We've got this axial group up, this axial group up, so they end up being cis, and this equatorial group is going to get pushed up above the ring, making all three cis. So let's look at the next example. So the next example, I've got two arms, down, up, and I've got an equatorial, an axial, and an equatorial. And for my 2D projection, just to make life easier, I'm going to start this as 1, 2, 2, and I would really suggest building it directly from the model with your modeling kit. So with the modeling kit, I've got an equatorial, an axial, and an equatorial. So this is my structure here. When I crush it, see it there. When I crush this down into a ring, I see that I've got two groups that are cis. So this group here and this group here are cis, and this back methyl group ends up being trans. So I get this going back, and this coming out. So how would I do that without a modeling kit? Again, I like to start with the axials because I think they're easier to see. So my first axial is up, down. This up is already filled in, so I'm just going to put a hydrogen. This hydrogen's up or down. This hydrogen's up. This hydrogen's down. Now, if I have any axials that are on the same side, so this is up, up, and up, these are all going to be cis. Any axials that are down, these are all going to be trans to any that are up. So since I'm just going to define this as anything up as being a wedge, this is going to get us, this third carbon here is going to get a wedge, and I don't have anything else in the axial positions. Now for the equatorials, it depends. If the hydrogen, if the axial group is pointing down, this will end up getting pushed up to make this above the ring. If the hydrogen is pointed up, this equatorial group will get pushed down when that hydrogen gets lowered, when this ring gets flattened out. So this will end up being below. So in this case, my axial will be above the ring. So this is where I get the wedge. And then when this hydrogen gets pushed down to kind of get us back into this ring, flat ring, this will get pushed down to give us the dash. Let's look at one more. So I've got out, up, and down. And we'll do 1, 2, 3. 1, 2, 3. Right, again, I'm going to highly encourage model building for these. So I take my chair conformation. I've got an equatorial, an axial, and a second axial. So I've built the model. So I got my equatorial coming off of carbon 1, 2 hydrogens in carbon 2, axial coming up for hydrogen 3, axial coming down for hydrogen 4, and then when I crush this ring down, come on, what I get is our 2 hydrogens going down, or 2 methyl groups going down, 1 methyl group going up. And so what I should get when I'm done is something that looks like this. All right, so how do I get to that without a modeling kit? Again, I'm going to go through and start by drawing the axial groups. So with 1, I have the axial going, hydrogen going up, down. This one's already occupied with a methyl group. This one's already occupied with a methyl group. Up, down. So any groups that are pointing, any axial groups that are pointing up, they're going to end up getting a wedge. So this is going to be a wedge. It's going to be up. Any that are down are going to get a dash, because they're going to stay beneath the face of this ring. So I've got, this is a wedge. So carbon 3 is a wedge. This is a dash. Now how about this methyl group on carbon 1? Well, since the axial starts above the ring, that's where it's going to finish, is above the ring, and so this is going to give us a dash. If there was this particular methyl group was on number 2, because this is beneath the ring, this methyl group is going to finish above the ring. So that's how you go from the 2G direction to the stereo drawing. Again, I would highly recommend the model building. The way I personally do it without a modeling kit is I take a look at the axial positions and figure it out from there. The axials, by the ones that are beneath the ring, they're going to be defined as dashes. The ones above the ring are going to be defined as wedges. And then that's kind of where you get this So anything that's a wedge has to be, the opposite of it has to be a dash. So since this is a wedge, the opposite of it has to be a dash. Since this is a dash, the opposite of it has to be a wedge. So the equatorial group ends up being a wedge. All right. Other question I got asked. Can you go over reactions of alkanes, page 24, and the NMR with alkanes, page 25? Oh, these are missing the lambda. That's good to know. So for these, what we're going to predict here is just halogenation. Alkanes are, quite frankly, the most boring class of organic compounds. They are bricks, they don't do anything. And I read a great critique in Chemical Engineering News one time about how we teach halogenation reactions of alkanes and don't bother to inform students that nobody does this because it's super hard to control. So if we have any alkane, C4H2N plus 2. And we can do this with rings, but we'll start with just the linear and branched alkanes first. And we run the reaction, some halogen, and there should be light above these so I can correct these on the keys. You'll end up getting CnH2n plus 1, Br plus HBr. And this is free radical halogenation. Now, this here is not really a very accurate statement. Typically what we get are successive halogenations, and it kind of becomes a cascade. Once we start halogenating, this compound becomes more reactive to successive halogenation, and we can talk about that when we look at the second example, which is BRT with cyclohexane. But the first one is going to look at this halogenation here. So we've actually got, that's why I like this example, is we've actually got all types of carbons in here. We've got a quaternary carbon, a tertiary carbon, a secondary carbon, and a whole bunch of primary carbons. Now, when we generate a free radical, it's stabilized by having more carbons around it, but we can't abstract a carbon, we have to abstract a hydrogen. So, quaternary carbons can't participate in halogenation reactions. This leaves us with primary, secondary, and tertiary. Now, tertiaries form the more stable radicals. And so what we expect for this compound is that this will be the point where the substitution occurs. And so we will get this compound here. Now, in reality, we are creating a stereocenter here. We have 4 groups, a Br, a methyl, an ethyl, and a tert-butyl. So we actually end up getting a mix of the R and the S. And that's important to note. For any halogenation reaction, we will get what's called a racemic mixture. We get a mixture of both the R and the S conformations for every single halogenation step. Because this free radical intermediate, when we do this reaction, we initially form a radical, and this radical is trigonal planar. It's flat. And the bromine radical can attack it from other sides. So if you got questions about that, definitely consult the notes on that. There's a lot better drawings for this. But what happens is we end up generating a bromine radical. The bromine radical takes the hydrogen off. This leaves a carbon radical. That's why we need the tertiaries. This tertiary radical is more stable than a secondary or primary. And we end up, because this is a trigonal planar radical, we end up with both the R and the S when we're finished. So we would correctly draw this as the starting compound with both a wedged and a dashed form of the bromine. Now, why is this not a particularly useful reaction? So if we look at the next one, this is cyclohexane. And what we'd expect for cyclohexane, these are all secondary carbons, there's no preference for one or the other, is at first we would form this compound here. And we don't have to worry about the wedge and the dash because there's no RS here. This is an achiral molecule. We have a hydrogen, a bromine, and then we have a ring left and right that look exactly the same. But once we've done this, we've converted a secondary carbon into a tertiary carbon. Well, this tertiary carbon is much better at stabilizing radicals than secondary carbons. So if we had sufficient energy to convert a secondary carbon into a brominated carbon, we definitely have sufficient energy to take a more stabilized carbon and convert it again. So really what happens here is we would get these two. We would get the dihalogenation product, because if we've got enough energy to stabilize a secondary radical, we definitely have enough energy to stabilize a tertiary radical. So what we end up getting here are runaway reactions. Basically, once you halogenate, you can't stop halogenating. It's very tricky to control these types of reactions, which is why industrially they're just simply not run. And you'll see this when we start working with alcohols and alkenes, is that we can pump alcohols and alkenes directly out of the ground, and they're a lot easier to work with. Plain alkenes like this, you're much better to combust. But if we limit ourselves and said we had the monohalogenation product, this would be the only thing we made, was the monobrominated product. But as the successive problems try to allude to, this is a hard to control reaction, and this is probably what you'd actually end up with more of, is the dibromo complex. Now the last one, the combustion of these. This is actually a problem, and I found it quite fascinating when I first started teaching organic, that students didn't actually know how to write or balance this reaction. So the other thing we can do with alkanes is burn them. So the question is, how do you balance this reaction? And a lot of students kind of get frustrated with this because they didn't know how to do it. And the thing is that you do know how to do it, you've just never seen it written like this before. So if I gave you a problem back in Chem 1 and said balance the following reaction, C6H12 plus O2 goes to CO2 plus H2O, you could easily solve this problem. You would say, well, there's 6 here, and 9O2 and not have issues. But the thing is that C6H12 is the formula for this compound. So the only tricky thing about combustion here is just converting this line bond drawing back into this C6H12. But you kind of already know how to do this. You know that there's 6 carbons, 1, 2, 3, 4, 5, 6. And you know that there's 2 hydrogens attached to each carbon because you only see 2 bonds. So it's 2, 4, 6, 8, 10, 12. And then you just balance the reaction as needed. All right. So the NMR problems. So we'll go with the one on page 26, since I think NMR is going to be the scarier one for y'all. The mass spec's pretty straightforward. You can go off the atomic weights. For the following problem, you're given a starting alkane that undergoes halogenation and the possible products. From the characterization, identify the correct product. And so here, we're getting bromination. There are 2 potential likely candidates for bromination here. Here, here, and here. More likely these 2 spots. But a secondary carbon is not necessarily an impossibility. And the table you're given says that you're given 1, 2, 3, 4, 5 chemical shifts, a quartet, a septet, a singlet, a triplet, and a doublet. So let's focus on the singlet for a moment. So if you've got a singlet, that means that, and the singlets are the easiest ones to find, you've got an area 3. So this singlet area 3 indicates an isolated methyl group, one that doesn't have any hydrogens adjacent to it. So if we look at this one, we've got a singlet from this pair, but this would be an area of 6 relative to the others. And we know it's not going to simplify because there's a hydrogen here with area of 1. So automatically we can discount this as a possibility because our singlet has the wrong area. If you look at this compound, here we have an isolated singlet of 3. So it has 3 hydrogens on that methyl group, and it's a singlet, so that's consistent with the table. So we haven't eliminated this one. Now if you look at this one, we don't have any singlets. These 2 methyl groups have an adjacent hydrogen. This methyl group has an adjacent hydrogen. This methyl group has an adjacent hydrogen. There are no singlets. So off the singlet signal alone, you can discount these two, but let's prove that we have signals for the other ones. So these two methyl groups will have an area of 6, and they're adjacent to one methyl group, so we expect to see a doublet. And if we look at the table, peak 5 is a doublet with an area of 6, so we do have a peak consistent with that. If we look at this one, this will have an area of 1, and it'll be a septet because it's got 6 adjacent hydrogens. So if we look at the table, peak 2 is a septet with an area of 1. If we look on the other side here, we've got an area of 2 with these two, and they see 2, so we've got a quartet. And so if we look at peak 1, that's an area of 2 with a quartet. And lastly, if we look at the final methyl group, this is going to have an area of 3, and it's going to be a triplet. And if we look at it, peak 3 has, or not peak 3, peak 4 has an area of 3 and a triplet. So when I talked about with NMR, we never go, it's really not useful to go from the molecule back, from the signal back to the molecule, because there's no uniqueness there. It's also a ton of work, and there's no proof that you're going to get like a single right answer. It's always approached with a starting guess. Well, this is what I mean, is that you've got 3 starting guesses here. You've got the one where the bromine's on the second carbon, third carbon, and then technically the second carbon, but you know what I mean, on the other end of the molecule. I always find singlets the easiest ones to identify. You're looking for isolated hydrogens. And so I try to count the areas of the singlets and the number of singlets and match those up first. Now, that's not always going to, this quickly gets you to a solution. Sometimes you'll eliminate just one possibility, but that's fine. Now that you've eliminated that one possibility, start looking for things like doublets. Doublets are easy to find because you're looking for something that's adjacent to one hydrogen. Do you have a carbon with just one hydrogen that's like next to like methyl groups? That's an easy way to get a doublet. So you start looking for self-consistency. Now, just because it worked for one, you need to go through and make sure all the others are correct, if anything, for just the practice. But generally speaking, that's how you approach these NMR problems, is you say, what do I expect to see based off all these models? Can I find a peak here in the table that corresponds to some part of this molecule? And that's why you had the discussion board where it said, okay, identify the 1H and the 13C signals based on this molecule, is so that you'll be prepared for problems like this. And the carbon 13 on the next page is the same way. If you have the double bromination of pentane, what do you expect to see? And what you're looking for here is, that one's also testing your ability, like can you predict correctly what the double halogenation should do? And also, can you predict where it's going to be? Because with pentane, there's actually 3 secondary carbons. And so any 3 of those secondary carbons are fair game. Now, it's not necessarily, there's 3 CH2 groups, there's 3 secondary carbons, don't necessarily look different under an NMR. So the other thing is like trying to see the symmetry. But yeah, you actually know how to do a lot of this. Page 28, same thing. Start looking for singlets. If you don't see singlets, start looking for simple splitting patterns like it says doublets and triplets. So look at the molecule and see if you can give something that would give that would give you a rise of a doublet and a triplet. Start eliminating these molecules based on the fact that you can or can't find a structure with some part of that molecule that would give rise to these splitting patterns. All right, so that's it for questions I've got asked. I've got the chat menu open in case anybody has questions. Again, these are not lessons or lectures. These are office hours. But I am here in case you have any questions. Doesn't look like anyone's in the chat anymore. So again, if you have any questions, please feel free to email in advance. These are not lessons, these are not lectures, these are definitely office hours. But again, we're free to answer any questions you have. So again, feel free to email any questions you have in advance or share the live streams, and I'll talk to you later.